Right away, I want to apologize if I have any spelling errors. I can't fix them. It's burned onto an NES cartridge. So this is, just want to quick do the special thanks, 2600 and Hope for actually getting me here, and Truth Fabian for actually paying to get me here, which is amazing. And just everyone on this list has helped out in more ways than I could possibly explain. And I do want you to notice right at the top it says NES cartridge. That will be important a little bit later. Okay, so who am I? I am a technology researcher, software engineer, web developer, and I co-founded and co-run a interactive technology studio called Black Pond Studios. And you'll probably see me solving Rubik's Cubes a lot. That's essentially what I do. It's my branding. So before this talk begins, it's a three-act presentation. The NES ROM is going to be made available. The source code will be available on GitHub. It's not available quite yet, but by the end of the conference, it'll be available. And the slides will be available as a PDF, so you don't have to run this on an NES emulator. And that's the website to go to, vigray.com/hopexii. That should be up by the end of the day. Also, before we begin, here's the bad sides of things. I am not an NES expert. If you want to know exactly how to program for the NES, go to the NES Dev Wiki or NES Dev forums. They know a lot more about this than I do. The F word is used in two proper nouns. I'm going to say the F word. And I can't guarantee this ROM or methods won't damage your NES. It probably won't, but I'm not going to make that guarantee. And the context for this, I ended up reading Proof of Concept or Get the Fuck Out, first F word, issue 14, which was a polyglot file. It was a PDF file, a zip file, and an NES ROM at the same time. I wanted to make an NES ROM that's also my resume. I couldn't. I thought that I needed to know more about NES development, and I fell into a rabbit hole. Turns out I didn't know about PDF files, and I didn't need to do the NES ROMs. But I'm here now. So I made an NES cartridge for the Toy Makers' Hackerspace. They developed this badge, and this was the cartridge. It required a Game Genie, which is why the presentation is called I Dream of Game Genies and Zip Files. And then I ended up making a NES ROM that was also a zip file that can be burned onto an NES ROM. So if you dumped the NES ROM, it would be a zip file that contains its source code. I wrote an article in Proof of Concept or Get the Fuck Out, issue 18, which just released a little later last month, I believe. And then also the programming language on this badge called TBAS, stands for Tis But a Scratch. It's based on the brainfuck programming language, or at least a derivative of it. I made an interpreter for it right here. So the first section's a hardware overview section, just kind of the stuff you need to understand for the interactivity section that'll come up a bit sooner, well, a bit later. The presentation's inside of one of those right now. There's a power button, a reset button, and 2 controller ports. Those will be a little bit more important a bit later on. This is the power button. You know it's the power button because it's the button that says power on it. It turns the system on and off. The reset button doesn't quite turn the system off and then on again, but mostly does that. It gets the game back to the beginning. This is a very crudely drawn controller. This is a more detailed controller. This is what the inside of an NES cartridge would look like. The CIC chip on the top left is the lockout chip. It keeps you from running a European NES game on a North American NES and vice versa. That chip's not going to be important for this talk. The other 2 chips, the CHR and the PRG chips, those will be very important in this talk. Remember, CHR, PRG. And that V and H on the bottom there will be a little bit important later on. Those chips at the CHR and the PRG are EPROMs, which stands for Erasable Programmable Read-Only Memory. These particular chips are the 27C256. The 256 stands for 256 kilobits, which is 32 kilobytes. I don't have much room for this. If you took a picture of the NES cartridge in my presentation with an iPhone 10, it'll be over 1,000 times bigger in file size than what I was allowed to use for this. So an NES ROM, so this isn't going on, well, this isn't the cartridge yet. This would just be a file itself. The first 16 bytes is an INES header. I'll explain that a bit later. Then the next 32 kilobytes are a PRG ROM. The next 8 kilobytes are the CHR ROM. Remember, the PRG and the CHR were both the EEPROM chips. Both of those are 32 kilobyte EEPROM chips. The CHR, though, is 8 kilobytes. So you would normally take the CHR ROM data and just repeat it 4 times to fill up that 32 kilobytes. I'll explain that a little bit later. So the CHR ROM is the graphical tile data. So this is what 1/2 of the CHR ROM will look like. And each of these big sections of tiles is called a pattern tile, well, a pattern table. Notice about 5 up, so you'll see the underscore, capital O, question mark, /. Above that is a blank tile. That'll be important. 1 second, gotta set up the emulator. I will go back to this a bit later. So the PRG ROM is the programming data. It's 6502 machine code, a nice 1975 chip. Tamagotchis actually used them until, I believe, the 90s, possibly into the 2000s for some weird reason. And it tells the NES console how to behave and think. The last 6 bytes, this isn't super important. Just know that I'm not allowed to really change the last 6 bytes too heavily, but it tells the program where to start and where important interrupts are. The interrupts part, not important for this talk. Just know that 6 bytes I can't really change. The INES header, that 16 bytes at the beginning, starts with capital N, capital E, capital S, and then the hex byte 1A, and then the value, well, hex value, in this case would be 2, and then 1 immediately afterwards. The 16-byte header specifies the length of the CHR and PRG ROM data. Tells the emulator how to handle NES files, and that NES 1A is a magic string. It says, hey, this file is an NES ROM. Emulators should pretty much immediately tell that it's an NES ROM. That 02 says that there are 16 blocks, well, there's 2 blocks of 16 kilobyte PRG, and the 1 says that there is a 1 8 kilobyte block of CHR. That's not super important, but it's required in the NES ROMs. There are 3 processors: the CPU, the central processing unit, that's based on the 6502 microprocessor; the PPU, which is the picture processing unit, it's essentially the graphics chip of the NES; and the APU, which is the audio processing unit. We're not going to talk about the APU. The CPU memory map, the first 2 kilobytes I have of working memory. This only has 2K memory. That is it. There's 8 bytes of PPU registers at hex 2000. It allows me to read and write with the graphics chip. And the last 32 kilobytes are the PRG ROM. All of that dumps from hex 8000 to hex FFFF. And then the last 6 bytes of that are those interrupts that I mentioned before. The PPU memory, the first 8 kilobytes are the CHR ROM that just gets dumped there. There's 4 kilobytes of name tables. I'll get to that in a little bit. And then there's palette data, just 32 bytes of that. Not going to get into that in this talk. So with that basic overview, I know it's a bit technical, but this should help for explaining the next section. This is interactivity. A lot of times when people think of interactivity with the NES, they will think of just pressing buttons. That's it. There are more things that the user can do to interact with an NES game that homebrew developers can program for. This is a crudely drawn Game Genie. This is a more detailed Game Genie. The Game Genie is a cheating device. It uses 6 or 8 letter codes, a maximum of 3 codes, and those are the letters. They're a little weird. It takes one address value of the PRG ROM and changes the value of that ROM. So you can patch the NES ROM a maximum of 3 bytes. And there's an optional key compare. So you can check to see if the value of that address byte was something in particular before you change the value. That's not super important, but so an example of a Game Genie code would be ZKPVLU. That takes the address E39B and changes whatever the value was to 4A. There's an 8-letter code example, ZKOVLULN. A lot of the same letters. That's because it takes the exact same address, the exact same value, but it'll only change it to that value if the key is, well, if the value was already 7B. So a demo of utilizing the Game Genie, you can require codes be used from a Game Genie in order to continue. In this case, I can't press A to go to the next screen. I have to use the Game Genie code GG next. Let's see if it works. Game Genie. GG. And, I'll take applause. GG next. Enter to the next slide. So this is a controller like before. There's the directional pads, so up, down, left, and right, a select, a start, an A, and a B button. That's usually what people think of when it comes to user input. The D-pad is the important one here. So the D-pad is a single button, just one solid button. The side view is a little hard to see, but it kind of is like a seesaw pattern. If you push one side down, the other side goes up. And each of the buttons have a separated circuit. So if you place something conductive in between it, the circuit can complete, and then the button gets pressed. So the seesaw design of the D-pad prevents up and down from being pressed at the same time, or left and right from being pressed at the same time. Conductive rubber pads. Can be a little hard to see, but there are these black little pads inside of these. These are conductive rubber. They will connect to... Where did the controller go? They will complete the separated circuits for all of these buttons. The controller can be taken apart, as you see. You can require someone to take apart their controller. To continue, press left and right on your controller. I cannot go to the next slide with this controller. Line this up. Left and... Let's see, do I have it plugged in? That will be... Probably have it plugged in. That will be more important. Not voltage spike. There we go. Left and right. So the controller can completely handle that, but the way the button is formed does not really allow that. This is the reset button. As I mentioned before, you can tell it's the reset button because it says reset. It forces the game to start from the beginning again. It's very similar to shutting the game off and starting it up again. The difference, though, is when you shut the game off and turn it on again, the memory resets. When you end up while pressing the reset button, the memory stays what it was since the last time, which is why you can reset Super Mario Bros. And your high score will stay the same. To detect resets on program start, check if a specified value you set is the same. So When the game starts, I will have it check, is a value a specific value? If so, the game was reset. After that point, it sets that value in memory to the value that it needs to be. So that's the way I can distinguish from a power on or a reset. To continue, press the reset button. One thing I really wanted to do with this talk, I wasn't able to, it was a little too ambitious, but I wanted to create a game, something where you can kind of set like a breadcrumb trail maybe. You continue forward. If you run into a dead end, you just reset back to the previous breadcrumb. You can actually prevent the reset button from working. You'll see that a little later. So there are name tables, like I mentioned before, 4 1 kilobyte name tables. They are the background tiles. This screen that you see is one name table. The background's actually 2 screens wide and 1 screen tall. So the camera of the screen at the moment is set to the X and Y coordinate 0, 0. That just says use the top left screen. The entire screen fills that up. It's basically like in a 3D game, the world is all around you, but the camera only sees so much. And the name tables are mirrored. So there are 4 name tables. These are the PPU values that they're all stuck in. It's just 1 kilobyte each. And when I say they're mirrored, either it'll be vertically mirrored, so the top left name table will be mirrored vertically to the bottom left, and the top right will be mirrored to the bottom right. So if I set something in either the bottom left or the top left, it'll appear in both. Horizontally mirrored is the same exact thing, except for it's horizontally mirrored instead of vertically mirrored. So hopefully it switches to my laptop. It might not. I hope it does. There we go. So this is an example. Let's see if I can get this. Okay, so Super Mario Bros. Is an example of vertically mirrored. So you can see it's the exact same tiles on the top half as it is on the bottom half. Balloon Fightin' is an example of horizontally mirrored, which is why if you go off the right side of the screen, you'll appear on the left side. Your sprite is copied onto both of them. So it's technically a copied clone of the balloon fighter that appears when you go off the side. Sorry for all the fumbling around. This is a slightly complicated setup. So mirroring, if you want to detect which mirroring this is, you can set the top left tile of the top left name table. In this case, you can see that they're all just blank tiles. That would normally be, in my case, the 0th position, or the first tile. I actually have it set for a space, like an ASCII space on the top left. I also have it mirrored onto whichever mirroring it has. I then check to see if the name table on the top right has the same tile value as the top left one. If they're the same, then it's horizontally mirrored. If it's different, it's vertically mirrored. So this is the cartridge again. That V and H, you can set the mirroring. This cartridge actually can detect that this is horizontally mirrored, which is weird because it says V right there, but I think that's vertical scrolling versus horizontal scrolling. But this detects what that little solder blob is. So this is a prototype cartridge. There's a little bit of solder that I had to put on one little blob on the bottom. This is able to determine which of those solder pads has a little solder blob on it. Region detection. There are 3 different regions that this came out for video-wise. NTSC, which is Japan and North America, it's 60 frame per video, well, 50 frame per second video. The PAL, which is the European region, was 50 frames per second video, but the CPU was slower than the NTSC version. Then there's the Dendy, which is essentially a Nintendo knockoff made from, I believe, Taiwan or Thailand, that was sold to a lot of the like Russian-related countries. And you can detect the region by counting the CPU cycles in a single video frame, which I will show in an emulator because I can switch the regions very easily on it. I have it set to European right now. They did this to us, we do this to them. We have updated our privacy policy. Your trust is very important to us. And if this is put onto a Famicom cartridge, the Japanese version of the NES, and put into a Dendy system, it puts up this message, Dendy, Dendy, we all love Dendy, Dendy, everyone plays, which translated to Russian was the saying they used in the commercials. I learned a lot about Russian telephone systems to get that first 4 digits of that phone number, because the commercial had the last 7 digits, but that number doesn't work anymore, hasn't worked since either 1996 or 2006 or something. But you can't buy a Dendy from that number anymore. Two input devices with a 3-way splitter is annoying. Cartridge detection. You can actually detect whether this is being played on a cartridge or if this is being played on an NES emulator. So the CHR uses 8 kilobytes like I showed in that overview slide, but the EEPROM is 32 kilobytes. You can set the CHR size to 32 from that INES header. You can fill all 32 bytes with whatever you want. Cartridge uses the last 8 kilobytes, and the emulator will use the first 8 kilobytes. See how well this works. Okay, so I can set, and it'll be a little hard to see. The first 8 kilobytes to test, I ended up setting all of the values of all of the tile datas to just 1s. The second set I set to 2s, the third set I set to 3s, fourth set I set to all 4s. When I burned this onto a cartridge and played it on an NES, all 4s showed up. When I played it on an emulator and tried on an EverDrive NES cartridge, all 1s showed up. That means I can stick whatever I want in the middle 16 kilobytes of the EEPROM, and the cartridge will read the last 8 kilobytes, and the emulator will read the first 8 kilobytes. Notice this says NES ROM file. I was going to make this, honestly, a completely different game if it ran on an emulator. You can do that. This can detect it. You can just have it run whatever you want. Sadly, I can't jump back to the beginning without pressing left and right on the controller again. So it can detect the tiles that you end up placing in the CHR data, because the CHR ROM the CHR data is stored in the first 8 kilobytes of the PPU, and you can read from there. An NES game can figure out what it looks like at any time. It can figure out what colors each pixel is. So in this case, for cartridge detection, the bottom right tile, that underscore, then capital O, question mark, /, the next value above that is blank. I have it looking like a very glitchy pixel. I'll show that in just a moment. Okay, same spot. It looks really glitchy there because I have it set as the hex values for the word emulator, but you can set it to whatever you want to. So this file is also a polyglot file. This is the more complicated section, so I apologize if I lose some of you with this section. A polyglot file is a file that exists as two or more distinct types of files simultaneously. And notice the word distinct. So essentially it would be like a zip file that if you changed the file extension to .jpg is also a picture of a cat. Some file types need to have the beginning bytes start at the start of the file. Some need certain bytes to end at the end of the file. There are a few file types that just really don't care. So some of them that have a strict start, an NES ROM, the first 16 bytes must be that NES header. JPEG has a header, bitmap, MP3. Flexible start and end. You can stick a zip file at the end of a file or in the middle of a file. It doesn't matter too much. 7-zip files and RARs will work very similarly. So this NES ROM, if I want to burn it onto a cartridge, the NES ROM will always be 65,552 bytes, which is 16 bytes more than 64 kilobytes. Unused PRG and CHR data is ignored, which means it's the perfect place to stick more data. So a zip file does not have a strict beginning or end for its file data. The header is essentially at the end of the file. It's called the end of central directory record and says where all of the file data is ahead of it. And there are offsets that say how far from the beginning certain file data is, so we can update that. Forgot to show one of the slides from my computer, so you get to see that now. So this essentially is the data that I'm actually storing on the NES ROM. The red, every time you see it, is where new data appears. The white is just unused space. So I'm really not using much space for most of this. I can stick a zip file right there. And it will run as a zip file. I'll show you that in a little bit. Expect a lot of switching back and forth for this. Just like the zip file, the 7-zip and RAR files do not have a strict beginning or end for its file data. And unlike the zip file, I don't have to worry about updating any offsets. I could stick a 7-zip file right there, RAR file right there. I don't need to worry about the beginning and end of it. It'll just work. Going a little ahead of myself. There we go. So extractors for 7-zip files and RAR files will usually also unzip the other sort of file and will unzip zip files and stuff. So it does get a little complicated. Because they open up so many files, a lot of times they ignore the extension and will just look to see what sort of data is inside the file first. In this case, the zip files data is first, so most of them will just open this up as a zip file. The command 7z with the flag T7z to say the type is a 7-zip file, and the X for extract will extract the 7-zip file, and unrar X will extract the RAR file. This is mostly a Linux thing, and I will show you the zip file, 7-zip, and RAR file. going to make a copy of the NES ROM. And I just renamed the copy to .zip at the end. So I can open this up as a zip file. And there are contents in this zip file, including a README that shows how to extract the rest of it. I'm going to change this to a 7-zip file. And I just extracted the 7-zip file. Let's see. Time for the RAR file. So that extracted the RAR file, and my resume's in there. I'm available for hire, by the way. But wait, there's more. So HTML files. They're very flexible. You can put a lot of data in there. You can mess up. I think they assume people are going to mess up. Any missing tags are quite often assumed by the browser. Extra data risks being interpreted as text. That's something that'll be a little important later. So there's extra data right at the top, and the div tags with hello world inside. If you run this text file in a browser by having a .html thing, it'll fill the rest of that data in. So you can set the body tag text to size 0 and the visibility to hidden. That'll make everything disappear. That inner div, you can then set the text size back to 16 pixels and the visibility to visible. That makes everything else disappear except for the data you want. Comment everything else because you might risk something being interpreted as a tag. So this is what the CSS would end up looking like. Oh, we'll get to brainfuck. Change that to .html. And it's a Game Genie encoder and decoder because I didn't really explain how the codes end up working. It's also a brainfuck interpreter, just in case. I'll get to that in just a little bit. I won't really have too much time to explain brainfuck. I apologize for that. Almost out of time. Turns out I'm really good at that programming language, and I hate myself for it. Video is wanting to be a little wonky. Let's see. I'll just run this on an emulator. Huh, no video. Anything weird on that side at all? There's the... It's frozen though. Plugging in. Crossing fingers. Is everything getting enough power? And right now it should be streaming from my laptop. Wrapped in from the laptop. Still nothing? Might be the box. So as I mentioned before, the HTML file, there's a brainfuck interpreter. Run the HTML file, well, that NES ROM, it is also a brainfuck file. But I wish I could show that a bit more, but the box does not seem to want to work. But I guess presentation's cut about a minute short. But the file will be available at vigray.com/hopexii. Anyone who feels like seeing the rest of the presentation, I suppose, just talk to me after. I'll be at the party. And yeah, that's an interesting way to end a presentation. I do want to mention that the zip file has a Python program in it that lets you split the PRG and the CHR data. I have more polyglots in there. The PRG file is also a bitmap image, and the CHR is also another NES ROM. But yeah, I'll just hit me up afterwards. I'll show you guys that. I actually have the second NES ROM is put on here. It's actually an album from a friend of mine. I told him if he learned Family Tracker, I'd put it on a cartridge.